Good afternoon, ladies and gentlemen. Can everyone hear me? Awesome. So I see there's already a question. So let me quickly get to those slides. I'm just quickly browsing to that slides. It should be this slide over here. So for this question, I would ask you to calculate lambda max for me. So if we want you to ask to calculate lambda max, then I will give you the temperature. So I would say something like a star is 6,000 degrees Kelvin. What will it lambda max be? And then you substitute that temperature in here, as easy as that. And then on the other way around, this is just the Stephen Boltzmann law. And it relates the temperature of a black body to the total radiated energy. So E is what we want. So this is a constant, omega, and I will give you the T that you need to calculate, and I will give you the constant. Or the other way around, I will give you E, you have the constant, and then you need to calculate the temperature. Does that answer your question? Awesome. So all of the questions will be straightforward plug and play. So yesterday we ended off with this slide of spectra, but now we're going to talk a little bit more about spectra. So I told you we have emission spectra, absorption spectra, but what we will realize is we have different kinds of spectra. And we can classify those spectra into three sub types. Will we get a formulas or should we? You will get a formula sheet with all the formulas and constants. So don't worry about that. I will give you a formula sheet. So there are three kinds of spectra that you guys will need to know, and that is continuous spectra, absorption or dark line spectra, which contain absorption lines, and emission or bright line spectra. So these are the three types of spectrum we are going to work with. And these kind of spectra are described by Kirchhoff's law. So Kirchhoff is also one of the brilliant physicists that has a lot to do with electromagnetism, so in spectra, but also in electrical engineering as well. Then Kirchhoff plays a big role. That's just on a side note. But now we are going to look at these three laws about spectra. And secondly, photons are emitted or absorbed when an electron in an atom makes a transition from one energy level to another. The wavelengths of photons depend on the energy difference between the two levels. So each spectral line represents not one energy level, but rather an electron jump between two energy levels. Hydrogen atoms can produce many spectral lines that are grouped in series, such as the Lyman-Boltzmann-Paschen series. Only 3 hydrogen lines, all in a Balmer series, are visible to human eyes. The emitted photons coming from a hot cloud of hydrogen gas have the same wavelengths as the photons absorbed by the hydrogen atoms and gases of a star. Most modern astronomy books display spectra as graphs of intensity versus wavelength. Be sure you recognize the connection between dark absorption lines, bright emission lines, and dips and peaks in the graphed spectrum. So this is the 3 types of spectra, and this is also Kirchhoff's 3 laws and the 3 types of spectra. So the first one is, so before we describe the laws, if we look at an object, we will see it in one of these 3 different spectra. So the first thing is a continuous spectrum. So that is a solid, a liquid, or a dense gas excited to emit light will radiate at all wavelengths, and this produce a continuous spectrum. So continuous spectrum will be like this absorption spectrum, but no gaps in between. So that means you'll see at all frequencies. Then the emission spectrum. Emission spectrum happens with a low density gas that's excited to emit light, will do at specific wavelengths, and this produces an emission spectrum. So remember, continuous spectrum is a solid, a liquid, or a dense gas. Emission spectrum is low density gas. And then absorption spectrum is if light comprising of continuous spectrum passes through a cool low-density gas, the result will be an absorption spectrum. So remember, a solid, a liquid, and a high-density gas is a continuous spectrum. A low-density gas that is excited will be an emission spectrum. And then when continuous light moves through a cool, low-density gas, that will be an absorption spectrum. You guys happy with these three definitions? Awesome. So this is just something interesting. You don't need to know this at all, but this is just interesting to show when we look at hydrogen. And hydrogen, we can get a few hydrogen lines. So that means emission spectrum such as this. So here, this corresponds to the Paschen series, and this as well to the Paschen series. Here's the Boltzmann series. This is the Lehman series. So this is just something interesting to show how these spectra will look like. So when we look at a stellar nursery or nebula like this, we can see the emission lines of hydrogen. So this is hydrogen alpha, beta. So here we can see this is the Paschen series looking at a wavelength in nanometers, and this is the Boltzmann series looking at their wavelength as well. Something interesting is physicists, especially astrophysicists and astronomers, like working in wavelengths. Engineers like to work in frequencies. You can switch easily from one to the other. So I personally like to work in frequencies. It just makes it a bit easier to understand. But traditionally, astronomy used wavelengths, but it's still the same thing. So for example, this would be a absorption spectrum. So here we will see the low density gas, the continuous light going through a low density gas, and here we can see the absorption spectrum. So that is very, very cool. So in image A, the sun spectrum at visual wavelengths. The bright colored background shows the continuous spectrum of blackbody emissions from the sun's photosphere. The dark spectral absorption lines represent precise colors, photons and energies removed from the sun's radiation by atoms in its transparent atmosphere. And then B, a model of the visual wavelength emissions, so the bright line spectrum of NGC 2329. And the nebula pictured in this chapter opening photo, and emission lines from ionized atoms, hydrogen, that's red, nitrogen, which is red, and oxygen is green, amongst others. And then in image C, graph of near-infrared spectrum of the atmosphere and surface of Saturn's moon Titan, measured by the Huygens probe at an altitude of 20 meters, using a light source at the bottom of the probe. So let's do an example of how we can look at these three different spectra as an example on one application. So imagine you are an astronaut with a handheld spectrograph approaching a fresh lava flow on a moon with no atmosphere. You aim your spectrograph straight at a lava flow. So which kind, so let's get something out to so you point your spectrograph straight at lava flow. So which spectrum do Kirchhoff's laws say you will see? So you'll get a continuous blackbody spectrum with all the colors of the rainbow present, given off by the opaque glowing lava. And the reason for that is it has to be a liquid, a solid, or a high density gas. So that is why we get a continuous spectra. And as a bonus, measuring the wavelength of the strongest blackbody emissions let you determine the temperature of the lava using Wien's law. So suddenly the lava flow begins to bubble and the gas trapped in the molten rock is released, making a temporary warm, thin atmosphere right above the lava flow. And if you point your spectrograph to look through the gas within the hot lava as the background, so remember you have to have a continuous color as the background, so hot lava as the background, and we can see it is a hot gas. So that means we will have an absorption, so dark line spectrum, in which lava's blackbody spectrum is now interrupted by missing colors, caused by atoms in the gas absorbing photons on their way from the lava to you. And finally, you crouch down and point your spectrograph at a gas at such an angle that the background is not lava, but cold, empty, dark sky. And now you will see an emission bright line spectrum produced by atoms in gas release photons as the electrons drop down towards the ground state, with lines at the same wavelength as the absorption of the same gas. So you guys happy how we went through this example and how we got the 3 different spectra? Awesome. So for a test and the exam, I can ask you what are the 3 kinds of spectrum, so just the definition, or I can give you an example like this, and then you have to tell me which kind of spectra can you see and why. So identifying the elements that are present in a star, planet, or gas could cloud by identifying the lines in an object's spectrum is a relatively straightforward process. For example, 2 dark absorption lines appear in the yellow region of the sun's spectrum at wavelengths 589 nanometers and 589.6 nanometers. The only atom that can produce this pair of lines is sodium. So the sun must contain sodium. So over 90 elements in the sun have been identified in this way. However, just because the spectral lines that identify an element are missing, you cannot conclude the element itself is absent. For example, the spectral line in the hydrogen-Balmer series are weak in the sun's spectrum, even though 90% of the sun atoms in the sun are hydrogen. So this is just the spectrum of the sun again. So to derive accurate chemical abundances, astronomers must use the physics that describe the interaction of light and matter to analyze a spectrum. Take into account the object's temperature and calculate the amounts of elements present there. Such results show that nearly all stars and most of the visible matter universe have a chemical composition similar to the sun's, so about 91% of the atoms are hydrogen and 8.9% are helium with small traces of heavier elements. So now the last thing we need to talk about in this set of lecture slides is the Doppler effect. So who of you are familiar with the Doppler effect? Okay, so quite a few. So let's go through it in any case, and please stop me if I can explain something better. So surprisingly, one of the pieces of information hidden in the spectrum is the velocity of the light source, and astronomers can measure wavelengths of the lines in a star spectrum and find the velocity of the star. This Doppler effect is the apparent change in the wavelength of radiation caused by the motion of the source. So when we look at this, Here we have a static car. So that means when you have your car horn or music playing from your car or your car alarm, these distances of these waves is equally spaced and you won't hear a difference. But as the car is moving in this direction and we are standing over here somewhere, we hear the sound coming in a more high-pitched tone because the car is moving. The waves are compressed. That means the distances is shorter, so shorter wavelengths, meaning higher frequency. If we are standing on this side and a car is moving, now the distance between the waves gets longer, meaning we have longer wavelengths, just then that means a lower frequency. And that is how the Doppler effects work. So when we analyze the wavelengths, it will look like this. When it's standing on this side, it will look like this. And this is the normal one. So that means our normal sound wave. Here we have longer wavelengths. Here we have short wavelengths. You guys understand this and is happy with it? Awesome. So this is exactly the same thing that happens in space when we look at the spectra of stars. So here for this analogy is a fire truck that we can see. Let's get a color out over here. So let's make this a little bit thicker. So as the fire truck is moving towards our direction and has its sirens on, it has a higher pitch, and at the back we have a lower pitch. When we look at a spectra of an object, the spectra isn't physically blue or red, it's just names we give it. So if it is blue shifted, it means the wavelength is compressed. If it is red shifted, it means the wavelength is longer. So when we denote in space something is blue shifted, then it's moving towards Earth. If it's red shifted, then it's moving away from Earth. Does that make sense? So on a side note, something we will discuss in a later chapter is that's one of the proofs that a universe is expanding because the entire universe is redshifted. So how it will look like when we look at a spectrum such as this absorption spectrum, on the bottom we can see that is a unshifted signal. So if it's redshifted, you'll see these absorption lines is started moved a little bit to the red part of the spectrum. So that is when they're redshifted, and here on the bottom when they're moving away from us, moving towards us. So redshifted is away from us, blue shifted is towards us. The spectrum lines is a little bit to the bluish part. So that is where the names blue shift and red shift comes from. But it's not the actual color, it's just we denoted those names. Does that make sense? Everybody happy with that explanation? Awesome. So this is just a example you can go through in your own time, how to use the Doppler effect. Sir, is light or sound? That will be light. There's no sound in space because sound needs a medium to propagate through, but light doesn't. So in space, it is the light of the star that we are looking at. So that means its spectrum. Awesome. So this is just the normal Doppler formula. So astronomers can measure radial velocity by using the Doppler effect. The laboratory wavelength, so lambda 0. So question, sir, up until what lecture number will we have to study for the test on the 24th of March? I will double check that. So I will make an announcement on ClickUp about that. So let's just check if I have a note somewhere. Let's see the study guide. Okay, so MES test 1, the 24th of March. March, which day is that? That is a Monday. So I will let you know. So that will probably be the work that we've covered up until that point. But I will let you know before the week before that, but I will let you know beforehand. So lambda is the wavelength is indicated a redshift. So delta lambda is positive if the wavelength is decreased a blue shift. And delta lambda is negative. And the radial velocity V of the star is given by the Doppler formula as below. So that is the radial velocity divided by the speed of light c is equal to delta lambda divided by delta lambda 0. So in astronomy, radial velocities are almost always given in kilometers per second. So c is expressed as 300,000 kilometers per second. For example, suppose the Libidori wavelength of a certain spectral line is 600 nanometers, and the line is observed in a star spectrum at a wavelength of 610 nanometers. That is delta lambda is plus minus 10 nanometers, and the radial velocity is 0.1 divided by 600 multiplied by the speed of light, which equals 50 kilometers per second. Because delta lambda is the positive, you know the star is receding from you. So this is just a straightforward plug and play question. So when you think about the Doppler effect, it is important to understand two things. Earth itself moves, so measurement of Doppler shift really measures the relative motion between Earth and the star. The second point to remember is that a Doppler shift is sensitive only to the part of the velocity directed away from you. So the radial velocity VR, you cannot use the Doppler effect to detect any part of the velocity that is perpendicular to your line of sight. So question, would we ever have to do conversions for units and tests? No, I won't do something. I will already give you everything in the correct units. So to keep it as simple as possible. Awesome. I see there are a hand raised. Is there something specific you want to ask? Okay, cool. So star moving to the left would have no blue shift or red shift because its distance from Earth would not be decreasing or increasing. This is why police using radar guns should park right next to the highway. They want to measure your full velocity as you drive towards them, not just part of your velocity. So there's an example how we would measure it. So you can go through this on your own time. Ladies and gentlemen, do you have any questions on what we've just done? Okay, so let's move over to our next set of lecture slides. So for this set of lecture slides, we are going to talk about the... So one thing and theme that we are doing through this entire course is, before we understand what's happening in the universe around us, we first try to study what is the closest to us. So the sun is a star, right? Yes. So before we can learn about other stars, we first need to learn about our own sun. And if we understand how our sun works, then we can use that knowledge to determine how stars work. So before we start with the sun, I want to show you a quick video.
The sun is a star. That's a profound statement. The sun is a star. That's a profound statement, and one that's not really all that obvious. Those little sparks in the night sky are pretty, but don't look anything at all like the hot blazing orb that lights up our days. It was a pretty remarkable intellectual leap to understand the sun and the stars are just different flavors of the same kind of object. The only difference is that the sun is close, but the stars are terribly far away, so they're fainter. Right away, let's clear up a misconception. A lot of people say the sun is a middle-sized average star, but that's not fair. Sure, it's somewhere in the middle of the size range of stars, but the vast majority of stars are dim red dwarfs, far smaller than the sun. By size and number, the sun ranks in the top 10% of stars in the galaxy. In our solar system, it's clearly the dominant object, brighter, more massive, and more influential than anything else. But what is it? The sun is essentially a big hot ball of mostly hydrogen gas. It's 1.4 million kilometers across, more than 100 times the Earth's diameter, and big enough that well over 1 million Earths could fit inside of it. And it's massive, 300,000 times more massive than the Earth, a staggering 2 octillion tons of gas. But if we want to truly understand the sun, we have to look into its heart. At the very core of the sun, conditions are hellish. The pressure is a crushing 260 billion times the Earth's atmospheric pressure, and it's a searing 15 million degrees Celsius. Under those conditions, hydrogen is completely ionized, which means the electrons in the atoms are stripped from their protons. This makes the core a thick soup of ultra-hot subatomic particles. In fact, the protons are squeezed together so hard by the octillions of tons of mass lying on top of them that an amazing thing happens. They fuse together. Through a complicated series of steps, the hydrogen atoms fuse together to form the heavier element helium. Along the way, some of the nuclear energy stored in those atoms is released. That amount of energy is described by Einstein's famous equation E = mc squared, which states that mass can be converted into energy and vice versa. Atoms are pretty small though, so each helium atom made in the sun's core generates only a tiny bit of energy, but a lot of helium atoms are made. A lot. Get this. Every second of every day, the sun converts 700 million tons of hydrogen into 695 million tons of helium. The missing 5 million tons, the equivalent weight of 15 Empire State Buildings, is converted into energy. And that's a lot of energy. Enough, in fact, to power a star. It's equivalent to detonating 400 billion 1 megaton nuclear bombs every single second. That's millions of times the entire nuclear arsenal of our planet, every second. And that's why, even from a distance of 150 million kilometers, the sun is so bright you can't even look at it. Even from that distance, its heat can be felt on your skin when you stand outside. Hydrogen fusion occurs in the core of the sun. The energy released heats the gas above the core, but not quite enough to fuse hydrogen into helium. Further from the sun's center, the gas becomes less dense, and at some point, the heat pouring up from below makes the gas buoyant. It rises in the same way a hot air balloon on Earth rises. This process is called convection. And it's an efficient way of transferring heat. Huge columns of rising hot gas stretch hundreds of thousands of kilometers high, bringing the sun's internal heat to the surface. The gas then cools and sinks back down into the interior. We can actually see the tops of these columns packed together across the sun's face. Above the convecting layer is a much thinner, cooler layer very near the sun's surface called the photosphere, or literally the sphere of light. This is where the density of the material inside the sun gets thin enough that it becomes transparent. Light can shine right through it. At this point, the energy from inside the sun is free to travel into space. It's this light that we see when we look at the sun. The sun is a gas and doesn't have a solid surface, but the gas in the photosphere thins so rapidly compared to the sun's huge size that you can think of it as the sun's surface. And there's one final layer above that, the ethereally thin corona, sort of like the sun's atmosphere. It's less than 1% as dense as the photosphere, but actually much hotter. Temperatures there can reach over 1 million degrees. However, it's so thinly dispersed that it's incredibly faint and can only be seen during a total eclipse or using special telescopes that block the intense light from the sun itself. The corona extends for millions of kilometers. And in a sense, it doesn't actually end. The corona merges into what's called the solar wind, a stream of subatomic particles moving away from the sun. It blows out in all directions, though mostly along the sun's equator. The speed of the wind is usually well over 1,000,000 kilometers per hour. Yes, seriously, and can reach speeds even much higher than that. When hydrogen fuses into helium in the sun's core, the energy is released in the form of light. This light immediately smacks into a subatomic particle, which absorbs it, converts a little bit of the energy into motion, and re-emits the light with a little bit less energy. The light works its way out of the sun this way, losing energy every time it encounters a particle, until eventually it gets to the surface and is free to fly away into the universe as a much lower energy photon of visible light. So how long does this process take? I've seen different numbers for it, some as much as 1,000,000 years. But a lot of those calculations don't model conditions inside the sun accurately. For example, they don't take into account the gas convecting for hundreds of thousands of kilometers. More modern calculations show that it takes closer to 100,000 or 200,000 years for the energy to work its way out. That's still a pretty long time. The light you see from the sun now got its start in the sun's core around the time Homo sapiens first appeared in Africa. The sun's surface is, to put it kindly, a mess. And the key to that mess is magnetism. I've been saying the sun is made of gas, but that's not entirely accurate. It's so hot inside the sun that electrons are stripped from their parent atoms in the gas, creating what's called a plasma, a gaseous soup of charged particles. We'll learn more about that in a later episode. But what's important now is the fact that a moving electric charge generates a magnetic field. The interior of the sun is essentially all charged particles in motion. Convection, coupled with the sun's rotation, sets up rivers or streams of plasma inside the sun, each generating and carrying its own magnetic field. When this plasma reaches the sun's surface, their magnetic fields do too. Maybe you've seen those looping arcs of magnetism around a bar magnet when it affects iron filings on a piece of paper. The solar magnetic fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even get tangled up. When the plasma reaches the surface, it cools. But if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe. Plasma shines because it's hot, but as it cools, it dims. It sits on the surface dimming, producing a dark spot on the surface of the sun, which we call a sunspot. Sunspots can be huge. They commonly dwarf the entire Earth, and some are so big they can be seen without using a telescope, as long as you're wearing adequate eye protection, of course. Around the edges of sunspots, the magnetic field lines are concentrated. This can energize the plasma even further, heating it up. This creates a bright rim around sunspots called faculae, Latin for little torch. The dark parts of sunspots dim the overall light from the sun, but faculae can be so intense they compensate for that and even add more light. Ironically, sunspots actually increase the energy output of the sun. Plasma on the sun's surface can flow along these magnetic loops too. This can create huge arcs of material called prominences or filaments, stretching for hundreds of thousands of kilometers across the sun, looking like fiery arches. We think these magnetic field lines are feeding energy from the sun's surface into the corona, which is why it's so much hotter. It's not exactly clear how this happens, but scientists are following several leads right now. This long-standing mystery may soon be solved. Magnetic fields on the sun also have a huge amount of energy stored in them. You can think of them like very tightly wound and very stiff springs. But remember, these magnetic field lines get tangled up. If conditions are right, they can actually snap, in essence creating a gigantic short circuit. When this happens, all that vast energy stored in the lines explodes outwards all at once in an event we call a solar flare. Even an average solar flare is mind-crushingly powerful. A big one can release as much as 10% of the entire sun energy output. This explosion blasts out high-energy light and launches material off the surface of the sun at high speeds, sending it into interplanetary space. Another type of solar eruption is called a coronal mass ejection, or CME. It's similar to a flare, but if a flare is like a tornado, intense and localized, a CME is like a hurricane, huge and strong. Like flares, they form when tangled magnetic field lines erupt, blasting out energy, but they occur higher off the sun's surface. Both flares and CMEs eject material into space. Billions of tons of it, in fact. This blast of debris can hit the Earth, and when it does, there can be profound effects. Our atmosphere absorbs the high-energy light, protecting us. Also, the subatomic particles are generally deflected by the Earth's magnetic field, so we're okay. But if conditions are right, The Earth's magnetic field can interact with the particles. Massive numbers are funneled down into Earth's atmosphere near the poles, causing the air to glow. This is what we call the aurora, or the northern and southern lights. Depending on the shape of the magnetic field, the auroras can form spectacular multicolored ribbons and sheets. Not all the effects are benign, though. As the magnetic fields interact, they can induce very strong currents of electricity in the Earth's crust. This can overload power grids, causing blackouts. In 1989, Quebec suffered a massive power outage from a solar storm. The very first such storm ever detected was in 1859, and it was also the most powerful ever seen. If an event like that were to happen today, it could cause worldwide blackouts and potentially be very damaging. Satellite electronics would be fried too, and we depend on those satellites for our modern civilization. In fact, in 2012, a huge storm, probably the equal of the 1859 event, blasted away from the sun in another direction, missing the Earth. Had it hit us, well, you probably wouldn't be watching this video now. We'd still be recovering. This is why studying the sun is so important. We depend on it for light and heat and the very basis of life itself, but it's entirely capable of knocking our society to its knees. Understanding it is critical to our future. The sun is the 2 octillion-ton gorilla in the room. We need to respect that. Today you learned that the sun is a star powered by nuclear fusion in its core. Hot plasma moves inside the sun, creating magnetic fields, which in turn can create sunspots, solar flares, and coronal mass ejections. These events can generate aurorae on Earth, cause power blackouts, and damage satellites. This episode is brought to you by Squarespace. The latest version of their platform, Squarespace 7, has a completely redesigned interface, integrations with Getty Images and Google Apps, new templates, and a new feature called Cover Pages. Try Squarespace at squarespace.com and enter the code CRASHCOURSE at checkout for a special offer. Squarespace. Start here, go anywhere. Crash Course Astronomy is produced in association with PBS Digital Studios. Go to their channel and find lots more awesome videos. This episode was written by me, Phil Plait. The script was edited by Blake DiPastino, and our consultant is Dr. Michelle Thaler. It was co-directed by Nicholas Jenkins and Michael Aranda, edited by Nicole Sweeney, and the graphics team is Thought Cafe. The Earth is a planet. That's a profound statement, and one that's not really all that obvious. For thousands of years, planets were just bright lights in the sky, one-dimensional points that wandered among the fixed stars. How could the Earth be one of them? With the invention of the telescope, those dots became worlds, and with spacecraft, they became places. The Earth went from being our unique home in the universe to one of many such, well, planets.
One giant leap for mankind.
The Earth is the largest of the terrestrial planets, the 4 smaller, denser, rocky worlds orbiting close into the sun. It's about 13,000 kilometers across and has a single large moon, which we'll learn more about next week. Unlike the other 3 terrestrial planets, Earth has something very important: water. Or more specifically, liquid water on its surface, where it can flow around, evaporate, become clouds, rain down, and then mix up chemicals so they can do interesting, complex things, like support life. Earth's ability to sustain life depends on that water. It also depends. Breathing has its advantages, and both, weirdly enough, depend on Earth's magnetic field to exist. And that in turn depends on what's going on deep inside our planet. So let's take a look. Like the sun, the Earth is a many-layered thing. At its very center is the core, which actually has 2 layers, the inner core and the outer core. The inner core is solid and made mostly of iron and nickel. These are heavy elements and sank to the center of the planet when it was forming, leaving lighter elements like oxygen, silicon, and nitrogen to rise to the surface. The solid inner core is about 1,200 kilometers in radius, or about 10% the radius of the Earth. The outer core is also mostly iron and nickel, but it's liquid. The material in it can flow. It's about 2,200 kilometers thick. The temperature in the Earth's core is tremendously high, reaching 5,500 degrees Celsius. The pressure is huge as well, as you might expect with the weight of an entire planet sitting on top of it. You might think at such a high temperature, iron would be a liquid, but iron can stay solid if the pressure is high enough. In the inner core, the pressure is extremely high, and even though it's hot, iron is solid. In the outer core, where it's still hot, but the pressure is a little bit lower, iron is a liquid. Above the core is the mantle. It's about 2,900 kilometers thick. The consistency of the mantle is weird. Most people think it's like lava, but really it's like very thick, hot plastic. It behaves more or less like a solid, but over long periods of time, geologic periods of time, it can flow. We'll get back to that in a sec. On top of the mantle is the crust, a solid layer of rock. The overall density of the rock in the crust is less than in the mantle, so in a sense it floats on the mantle. There are two types of crust on Earth: oceanic crust, which is about 5 kilometers thick, and continental crust, which is a much beefier 30 to 50 kilometers thick. Still, the crust is very thin compared to the other layers. The crust isn't a solid piece though. It's broken up into huge plates, and these can move. What drives the movement of these plates is the flow of the rock in the mantle, and that in turn is powered by heat. The core of the Earth heats the bottom of the mantle. This causes convection. The warmer material rises. It's not exactly a speed demon though. The rate of flow is only a couple of centimeters per year, so it takes about 50 or 60,000 years for a blob to move a single kilometer. The hot material rises toward the surface, but it's blocked by the crust. The magmatic rock pushes on the plates, causing them to slide around very slowly. Your fingernails grow at about the same rate the continents move. Over millions of years though, this adds up, changing the surface geography of the Earth. Where you see the continents now is not at all where they were millions of years ago. In some places, generally where the plates come together, the crust is weaker. Magma can push its way through, erupting onto the surface, forming volcanoes. Other volcanoes, like Hawaii or the Canary Islands, are thought to be from a plume of hotter material punching its way right through the middle of a continental plate. As the plate moves, the hotspot forms a linear chain of volcanoes over millions of years. Volcanoes create new land as material wells out, but they also pump gas out of the Earth too. A large part of Earth's atmosphere was supplied from volcanoes. The interior of the Earth is hot. In the core, it's about as hot as the surface of the sun. Where did that heat come from? Most of it is left over from the Earth's formation more than 4.5 billion years ago. As rock and other junk accumulated to form the proto-Earth, their collisions heated them up. As the Earth grew, that heat built up, and it's still toasty inside even today. Also, as the Earth formed and gained mass, it began to contract under its own gravity, and this squeezing added heat to the material. Another source is elements like uranium deep inside the Earth, which add heat as the atoms radioactively decay. And a fourth source of heat is from dense material like iron and nickel sinking to the center of the Earth, which warms things up due to friction. All of these things add up to a lot of heat, which is why, after all these billions of years, the Earth still has a fiery heart. The outer core of the Earth is liquid metal, which conducts electricity. The liquid convects, and this motion generates magnetic fields, similar to the way plasma in the sun generates magnetic fields. The Earth's rotation helps organize this motion into huge cylindrical rolls that align with the Earth's axis. The overall effect generates a magnetic field similar to a bar magnet, with a magnetic north pole and south pole, which lie close to the physical spin axis poles of the Earth. The loops of magnetism surround the Earth and play a very important role. They deflect most of the charged particles from the solar wind, and they trap some too. Without the geomagnetic field, that solar wind would hit the Earth's atmosphere directly. Over billions of years, that would erode the Earth's air away like a sandblaster stripping paint off a wall. Mars, for example, doesn't have a strong magnetic field, and we think that's why its atmosphere is mostly gone today. But we do have an atmosphere, and it's more than just air blowing around. Earth's atmosphere is the layer of gas above the crust. Because it's not solid, it doesn't just stop, it just sort of fades away with height. By accepted definition, and by that I mean it's not really science, it's more of a, let's just do it this way kind of a thing. The line between Earth's atmosphere and space is set at 100 kilometers up. This is what's called the Kármán line, and if you get above it, congratulations, you're an astronaut. The atmosphere is, by volume, about 78% nitrogen, 21% oxygen, 1% argon of all things, and then an assortment of trace gases. There's water vapor too, almost all of it below a height of about 8 to 15 kilometers. This part of the atmosphere is warmest at the bottom, which means we get convection in the air, creating currents of rising air, which carry water with them, forming clouds, which in turn is why we have weather. At a height of about 25 kilometers on average is a layer of ozone, a molecule of oxygen that's good at absorbing solar ultraviolet light. That kind of light can break apart biological molecules, so the ozone layer is critical for our protection. Incidentally, the Earth's magnetic field does more than trap solar wind particles. It also channels some of them down into the atmosphere, where they slam into air molecules about 150 kilometers up. This energizes the molecules, which respond by emitting light in different colors. Nitrogen glows red and blue, oxygen red and green. We call this glow the aurora, and it happens near the geomagnetic poles, far north and south. The lights can form amazing ribbons and sheets, depending on the shape of the magnetic field. I've never seen an aurora. someday. You may not be aware of the atmosphere unless the wind is blowing, but it's there. It exerts a pressure on the surface of the Earth of about 1 kilogram per square centimeter, or nearly 10 tons per cubic meter. There's roughly a ton of air pushing down on you right now. You don't feel it because it's actually pushing in all directions, down to the sides, even up. And our bodies have an internal pressure that balances that out. The Earth also has liquid water on its surface, unique among the planets. The continental crust is higher than oceanic crust, so water flows down to fill those huge basins. The Earth's surface is about 70% covered in water. Most likely, some of this water formed when the Earth itself formed, and some may have come from comet and asteroid impacts billions of years ago. The exact proportion of locally sourced versus extraterrestrial water is still a topic of argument among scientists. Earlier, I mentioned trace molecules of gas in the atmosphere. One of these is carbon dioxide, which only constitutes about 0.04% of the lower atmosphere, but it's critical. Sunlight heats the ground, which emits infrared light. If this infrared light were allowed to radiate into space, the Earth would cool. But carbon dioxide traps that kind of light, and the Earth doesn't cool as efficiently. This so-called greenhouse effect warms the Earth. Without it, the average temperature on Earth would be below the freezing point of water. We'd be an ice ball. This is why climate scientists are concerned about carbon dioxide. A little is a good thing, but too much can be very dangerous. Since the Industrial Revolution, we've added a lot of the gas to our atmosphere, trapping more heat. By every measure available, the heat content of the Earth is increasing, upsetting the balance. It's melting glaciers in Antarctica and Greenland, as well as sea ice at the North Pole. Sea levels are going up, and some of the extra CO2 in the air is absorbed by the oceans, acidifying them. There's an old concept in science fiction called terraforming, going to an uninhabitable alien planet and engineering it to be more Earth-like. I don't know what the opposite process would be called, but it's what we're doing to Earth right now. The Earth is the only habitable planet in the solar system. And you know what? We should keep it that way. Today,
So hopefully that provides a bit of an overview. So before we begin, I want to ask a question. Are you guys familiar with the Parker Solar Probe that was recently launched? So the Parker Solar Probe was a probe that is our closest attempt to the sun. So before we start, I'm going to show you a video about the Parker Solar Probe, and then we will continue on with our lecture slides.
Scientists put a vision that we need to fly a spacecraft within the atmosphere of the sun. But it is so challenging, extremely difficult to realize that it took us 6 decades to build a system that can fly safely and reliably within the atmosphere of a star.
3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the sun.
It looked like we had a hit there for a second.
Yes, Nick. I believe we do have a detection of beacon tone 1.
There it is. See it? There it is.
Parker Solar Probe is
3.8
million miles from the surface of the sun.
It is so incredible to just realize this is the moment that we designed this mission for. 3.8 million miles may not sound that close, but if I put the sun and the Earth 1 meter apart, Parker Solar Probe would be 4 centimeters from the sun. It's the closest human-made object to a star and also the fastest, traveling at 430,000 miles an hour. I mean, we're flying through the atmosphere of a star. That's not easy to do. It's something we've never done before.
This is our first close encounter with a star, and it's really just amazing. This area that Parker is going into is just so crucial to our understanding of the sun and its impact on the Earth.
That solar interaction, that space weather, those billions of tons of material that the sun can throw at us interacts with our power grids, can interact with our technology. So it's really important to understand them at their source and how they get all that energy.
When we were thinking about designing a spacecraft to go to some place that had never been before, and it's actually going there to study the sun. And so you're kind of saying, what am I designing? What are the environments it's designing for?
It has to go from the deepest, coldest space to a very warm area and keep everything working at a little bit above room temperature.
It's designed to go to such an extreme environment. You look at it and it doesn't quite look like most other spacecraft. The whole thing is designed such that the heat shield is taking most of the brunt of the heat of the sun. The heat shield will be at about 1800 degrees Fahrenheit, and it's protecting the spacecraft. So the spacecraft's actually basically at room temperature.
This is such a great feat of engineering, and it really shows how capable we are in space.
This is something that we've been wanting to do since 1958 when it was first mentioned, and the technical problems that had to be overcome in order to achieve it, it's just monumental to be able to get a spacecraft this close to the sun.
To get close to the sun is not easy. It looks like from Earth to the sun, not that far. The key issue is energy. In order for Parker to get close to the sun, we needed to lose a lot of Parker's speed possessed at Earth's orbit. Fortunately, I was able to create a trajectory with 7 Venus flyby.
The mission uses Venus in order to actually change its angular momentum and slow down to actually go closer and closer to the sun.
Over the course of about 6 years and the 7 flybys, we were able to move closer to the sun, and each time unraveling a little bit more of the mysteries of the sun as we get data from places that no spacecraft has ever been before.
It's the only star in our galaxy that we can actually go visit, and that's what makes it so magical.
By flying within the atmosphere of the sun, we are basically tracing the fingerprints of the physical mechanisms of the sun. We now view the sun in a different way. When you look at images from Parker Solar Probe, oh my goodness, they are extremely, extremely complex. And that complexity, for us, it's a new science that we need to investigate, we need to understand.
The things that we've learned over the years that Parker has been in orbit have been amazing. They've challenged our ideas about how the solar wind is made, about how the sun works, about some of these fundamental things that are going on.
There's a lot of pride and excitement for this closest approach. So much effort and so many people have worked on this.
I think it really took the teamwork and synergy of engineers and scientists and administrators and a lot of different people to think this mission up.
It makes you think that you can basically overcome any hurdles. So dream big, make it happen.
So that is really cool. So a question, what's the difference between a star and a planet? So a planet is such as Earth, Venus, Jupiter. So that planet is a smaller object that orbits around a star, and a star is like our own sun. So does that answer your question? In Sir, is Stephenson 2018 really further away? Yes, it's much further away, but also very, very bigger than our own sun. Then another question, will we also learn about a solar wind in later chapters? So yes, we will learn about the solar wind actually in this lecture. So this lecture is entirely about our own sun. So we will learn about the sun as a whole and what makes the sun tick. So the solar's atmosphere, photosphere, corona, solar corona, what the composition of the sun is, its stages and cycles it goes through, the solar wind, how it fuses energy. So this is going to be a very thorough understanding of what the sun is. So I want to start out with this image. Do you guys know what this is? Shooting out of our own sun. Yes, that is a solar flare. So that is an eruption on the sun's surface. that ejects matter, and that's through the magnetic field lines of the sun is being pulled back in. And we are going to talk about that quite a lot in this lecture. So for this lecture, we need to answer 4 fundamental questions. And one is, what can you learn about the sun by observing its surface and atmosphere? Secondly, what are dark sunspots? Thirdly, why does the sun go through 11 and 20-year cycles of activity? And lastly, what is the source of the sun's energy? So I want to ask you, this is a picture of the sun, but what is that on the sun? Not a sunspot, not Venus. So here we can see 2 small sunspots, one over here, one over there. But this that we are seeing over here is the planet Mercury that's transiting in front of the sun. Because it orbits so close to the sun, we can actually see it moving in front of the sun, which is very, very cool. So we can see transits of Mercury and Venus in front of the sun. The Mercury transits we can see actually quite regularly. So scientists joked that solar astronomers would know a lot more about the sun if it were further away. The sun is so close that Earth's atmosphere can see swirling currents of gas and arch bridges of magnetic force at a level of detail that seems overwhelming. The sun is made up almost entirely of hydrogen and helium gas, confined by its own gravity in a sphere 109 times Earth's diameter. The gases of the sun's atmosphere are hot and radiate the light and heat that make life possible on Earth. So something I want to emphasize is, in this diameter of the sun, we can fit 109 Earths next to each other. So the sun is big. So just to put everything in a bit of perspective of how big the sun really is. So, the image of what is this? Any ideas? No. This is an image of the sun taken from the surface of Mars from the Curiosity rover. So isn't this an amazing image? So question, sir, how does heat work in space? Like, is there a point in space close to the sun in which you could actually feel warm and not melt? Or is it a concept that only applies in Earth's atmosphere and in space? You get energy that isn't warm. So no, that is actually good. So for example, when you have the International Space Station around Earth, when it is in direct sunlight, it's actually a couple of 100 degrees warm because you have no atmosphere protecting you. And if you're now moving the International Space Station orbits around Earth, and you are orbiting in the shadow of Earth, then it's actually minus a couple of 100 degrees. So you have to insulate everything. So yes, our atmosphere plays a big role. So the closer you are to the sun, the warmer you are, and the further away you are, the cooler it is. So yes, Mars is further from the sun than Earth's. So what is this image? The sun from where? So this is the sun from Saturn. You guys are correct. And this is one of the most important photographs ever taken in astronomy. So when the Cassini spacecraft flew past Saturn, the astronomer Carl Sagan that I've talked about suggested, why don't they turn the cameras around and see how the sun looks like? So something interesting about this photo is, yes, these white are the rings of Saturn. You are correct. So something interesting is, what is this in the image? Yes, that is Earth. So here's the sun, and that is Earth. So if you Google this is known, the image is known as the pale blue dot, and is one of the most famous and probably one of the most important images in astronomy. So the sun's atmosphere is made out of 3 layers. The visible surface is the photosphere, and above that are the chromosphere and the corona. So why are we visible but not Venus or Mars? That just depends on the orientation of the stars and the angle at which it is taken. So yes, Venus and Mercury we should be able to see, Mars perhaps, but it was just how the image was set up. So in this image only Earth was in focus. So something interesting is, before we continue, did you know our sun actually has another name? Or let me say, what is the official name of the sun? And the sci-fi fans, yes, Matthew, you are correct, Sol. So Sol is Latin for sun. So that is why we are the solar system, or when you translate directly, the system of Sol. Or when you watch Star Trek, they speak about the Sol system. So that's the name of our sun and our solar system, the Sol for solar in Latin. So now that astronomers normally speak of the interior of the sun as being below or under the photosphere, and the sun's atmosphere as being above or over the photosphere. When you look at a sun, you see the photosphere as a hot glowing surface with a temperature of about 5,800 degrees Kelvin. And that temperature is determined by precisely measuring the spectrum of sunlight, then using Wien's law. At that temperature, every square millimeter of the sun's surface is radiating more energy than a 60-watt light bulb. With all that energy radiating into space, the sun's surface would cool rapidly. If energy did not flow up from the interior to keep the surface hot. So simple logic tells you that energy in the form of heat is flowing outward from the sun's interior. And not until the 1930s did astronomers understand that the sun makes its energy by nuclear reactions at its center. The visible surface of the sun looks like a smooth layer of gas marked only by a few dark sunspots that came and go over a few weeks. Although this photosphere seems to be a distinct surface, it is not solid. In fact, the sun is gaseous from its outer atmosphere right down to its center. The photosphere is a thin layer of gas from which Earth receives most of the sunlight. It is less than 500 kilometers deep, and a model of the sun, the size of a bowling ball, the photosphere would be none thicker than a layer of tissue paper wrapped around a ball. The photosphere is the layer in the sun's atmosphere that is dense enough to emit plenty of light, but not so dense that light can't escape. Below this photosphere, the gas is denser and hotter and therefore radiates plenty of light. But that light cannot escape because it's blocked by the outer layers of gas. Earth does not receive light from deeper layers under the photosphere. In contrast, the gas above this photosphere is less dense. So although Earth does receive that light, there is not much of it. This photosphere appears to be substantial, but is really very low density gas. Even in its deepest and densest layers. The photosphere is less than 1/3000th as dense as the air you breathe. To find gases as dense as the air at Earth's surface, you would have to descend about 15,000 kilometers below the photosphere. With fantastically efficient insulation, you could fly a spaceship right through the photosphere, what the Parker Solar Probe actually did. So some of the sci-fi fans, the spacecraft of what is this, or who is this spacecraft? So let's get a better image. Star Trek, yes. So this is the Starship Voyager. So let's say we were all in the Starship Voyager. Let's go a slide back, and we were in the orbit around the sun, and we start to study the sun. What would we see, or what would we observe? So when we put this into perspective, when we look at the sun, the photosphere is right here. So this photosphere is the sun's atmosphere. And this is the chromosphere, so the photosphere, the chromosphere, and when we block out a sun, such as in a eclipse, this extension we see around it is the corona. So something that is quite astonishing, and one of the reasons why the Parker Solar Probe was launched is the corona around the sun is much, much, much warmer than the sun itself. And we have no idea why that is. We have a leading theory that we will discuss in a moment, but we have no idea why the corona is hotter than the rest of the sun. And that is one of the main reasons why the Parker Solar Probe was sent to investigate. So we all know the spectrum of the sun, and we learned about this image, correct? Yes. So we know from Kirchhoff's third law that an absorption spectrum is produced. The source of a continuous blackbody spectrum is viewed through a transparent gas. As a photosphere are dense enough to produce a continuous spectrum. So atoms in the higher transparent layers of the photosphere and in the sun's atmosphere absorb photons with unique wavelengths and energies corresponding to the jumps between each type of atom's electron orbits, producing absorption lines that allow you to identify hydrogen, helium, and other elements. In good photographs, the photosphere has a bolted appearance because it is made up of dark edge regions called granules. The overall pattern is called granulation, and granules can be several thousand kilometers across, but last only for about 10 to 20 minutes each before fading, shrinking and being replaced by a new granule. Detailed observations of the granules show that their centers emit more black body radiation and are slightly bluer than edges. From this information, plus the Wien and Stephen Boltzmann laws, astronomers can calculate that the granule centers are a few hundred degrees hotter than the edges. Convection occurs when hot material rises and cool material sinks, as when, for example, a current of hot gas rises above a candle flame. You can watch convection in a liquid by adding a bit of cool non-dairy creamer to an unstirred cup of coffee. The cool creamer sinks, gets warmer, expands, rises, cools, contracts, sinks again, and so on, creating a small region on the surface of coffee that marks the top of convection currents. Viewed from above, these coffee regions look something like solar granules. The presence of granulation is clear evidence that energy is flowing upward through the photosphere. So when we talk about convection, a good example is when you are making porridge on your stove. So when you have your porridge pritting on your stove, you'll see there's pieces of your porridge that moves upwards. So that means warm currents is taking it up. And then in a couple of seconds, it cools down again and it sinks to the bottom of the pot. And you can see that with porridge and by making some other stuff or cooking other stuff as well. But that is a good example of convection. So spectroscopic studies of the solar surface has revealed another less obvious kind of granulation, and that is supergranules, and are regions a little over twice Earth's diameter that include about 300 granules each. These supergranules are regions of very slow rising currents that last a day or two. They appear to be produced by larger gas currents that lie deeper under the photosphere than the ones that produce the granules. So when we look at the sun's surface, we will see this in the figure above. But as we determine what it is, these granules, we can see it is rising gas and sinking gas. So warm rising gas rises up, and then it cools down at the surface, and it sinks back down again. Does everyone understand granules and convection? Awesome, because that is quite an important aspect that you guys need to understand. So above the photosphere lies the chromosphere. So solar astronomers define the lower edge of the chromosphere as lying just above the visible surface of the sun, with its upper regions blending gradually with the corona. You can think of the chromosphere as an irregular layer with a depth average less than Earth's diameter. Because the chromosphere is roughly 1,000 times fainter than the photosphere, you can see it with your unaided eyes. And only during a total solar eclipse, when the moon covers the brilliant photosphere, then the chromosphere flashes into view as a thin pink layer just above the photosphere. The pink color is produced by the combined light of three bright emission lines, the red, blue, and violet Balmer lines of hydrogen. The chromosphere produces an emission spectrum, and Kirchhoff's second law tells you it therefore must be an excited, low-density gas. Further analysis of solar spectra reveals that atoms and the lower chromosphere are ionized, and atoms in the higher layers of the chromosphere are even more highly ionized. So astronomers can find the temperature in different parts of the chromosphere from the amount of ionization. Just above the photosphere, the temperature falls to a minimum of about 4,500 Kelvin, and that rises rapidly to extreme high temperatures of the corona. And the upper chromosphere is hot enough to emit X-rays and can be studied by X-ray telescopes. That is why I said the corona is much, much warmer than the rest of the sun. A photogram is an image of the sun made using light only at wavelengths of one of those strong absorption lines to reveal detail in the upper regions of the chromosphere. Another way to study these layers of gas high in the sun's atmosphere is to record solar images in the far ultraviolet or X-ray portions of the electromagnetic spectrum. Because those layers are very hot and emit most of their light at short wavelengths. So the following figure shows a photogram made at wavelength of the alpha hydrogen Balmer line. This image shows complex structures in a chromosphere, and in spicules of flame-like jets of gas extending upwards into the chromosphere and lasting 5 to 15 minutes. So here we can see these spicules. So in image A is an hydrogen alpha photogram of the sun's disk. And then in image B, hydrogen alpha photograms reveal complex structures in the chromosphere that cannot be seen in ordinary visual wavelength images, including spicules springing from these edges of the supergranules. Then in image C, seen at the edge of the solar disk, spicules look like burning prayer, but are not all related to burning. So these little filaments you see standing up, Those are the spicules that we are seeing. So question, please, may you explain slide 20 again? So let me go back to slide 20. So yes, when we look at the sun's surface, we see these structures on the sun's surface. But when we are analyzing it, that actually is granules. And the granules is warm gas rising up, then it reaches the surface, then it cools down and it sinks down again. So here it rises up, gets to the surface, cools down, sinks down again. So that is just the pattern that convection makes. Does that answer your question? Yeah, so I assume so. So the outermost part of the sun's atmosphere is called the corona. So after the Greek word for crown, the corona is so dim that, like the chromosphere, it is not visible in Earth's daytime sky because of the glare of the scattered light from the sun's brilliant photosphere. So during a total solar eclipse, the innermost parts of the corona are visible to the unaided eye, and that is what we are seeing here. So something interesting, for those of you that is very interested in the sun, there's a branch of physics and astronomy called heliophysics that is concerned with studying the sun. So I know the Northwest University has a very strong research focus on heliophysics as well. So that is just something to consider for those of you that wants to study the sun for master's or PhD, for example. The observations made with specialized telescopes called coronagraphs can block the light of the photosphere and record the corona out beyond 20 solar radii. So almost 10% of the way to Earth. So such images reveal streamers in the corona that follow magnetic lines of force in the sun's magnetic field. The corona spectrum, like that of the upper chromosphere, includes emission lines of highly ionized gases. In the lower corona, the atoms are not highly ionized as they are higher altitudes. And this tells you that the temperature of the corona rises with altitude. Just above the chromosphere, the temperature is about 500,000 Kelvin. But in the outer corona, the temperature can be 2 million Kelvin or more. So the corona is hot enough to emit X-rays, but the coronal gas is not very luminous because its density is low. So let's discuss this a bit. So in the top two images, two nearly simultaneous images, so sunspots in the photosphere and excited regions in the chromosphere above the sunspot. So when we look at visual wavelengths, we can see these sunspots, and we will discuss that in a moment, but in the areas above those sunspots in ultraviolet, we can see the sun is more turbulent and more violet. And then in these images below, we can look at, this is a false color images in both. We have these specialized cameras that we call the chronographs that block out the sun itself, and then we can observe the corona around the sun. Astronomers have wondered for years how the corona and chronosphere can be so hot. Heat flows from hot regions to cool regions, never from cool to hot. So how can the heat from the photosphere with a temperature of only 5,800 Kelvin flow out into the much hotter chromosphere and corona? So observations made by the SOHO telescope, that stands for the Solar and Heliospheric Observatory Satellite, have mapped a magnetic carpet of looped magnetic fields extending up through the photosphere. Because the gas and the chromosphere and the corona is very low densities, it can't resist movements of the magnetic fields. Turbulence below the photosphere seems to flick the magnetic loops back and forth and whip the gas about, heating the gas. Furthermore, observations within the high node, Hinode 8 spacecraft have revealed magnetic waves generated by turbulence below the photosphere, traveling up into the chromosphere and corona and heating the gas. In both cases, energy appears to flow out from the interior of the Sun to the chromosphere and corona, not by radiation, but by agitation of the magnetic fields. Ionized low-density gas cannot cross magnetic fields, so where the Sun's field loops back to the surface, the gas is trapped. However, some of the magnetic fields lead outward in space, and there the gas flows away from the Sun in the solar wind that can be considered an extension of the corona. So because the solar wind, the Sun is slowly losing mass, but this is a minor loss for an object as massive as the Sun. So the Sun loses about 1 million tons per second of mass, but compared to the size, that's only a fraction of it. So another thing about the solar corona and Earth's magnetic field. So Earth has a magnetic field that protects us from the dangerous solar wind. But we will discuss that in a later chapter. So now we need to talk about the composition of the Sun. So it seems as though it should be easy to learn the composition of the Sun just by studying its spectrum. But this is actually a difficult problem that wasn't well understood until the 1920s. The solution of that problem is the story of an important American astronomer who waited decades to get proper credit. So is the loss of mass regenerated? Yes, that is regenerated again by fusion that we will discuss in a moment. In her 1925 PhD thesis work, Cecilia Payne invented modern methods of interpreting spectra of the Sun and stars. For example, sodium lines are observed in the Sun's spectrum, so you can be sure that the Sun's atmosphere contains some sodium atoms. Payne comes up with a mathematical procedure to determine just how many sodium atoms are there. She also proved that if spectral lines of a certain element are not detected in the Sun's spectrum, that element might still be present, but a gas is too hot or too cool or the wrong density for the type of atom to have electrons in the right energy levels to produce visible lines. Payne's first calculation showed that over 90% of the Sun's atoms in the Sun must be hydrogen, and most of the rest are helium in contrast. Atoms like calcium, sodium, and iron have strong lines in the Sun's spectrum are actually not very abundant. So question, what do you mean fusion? Do you mean the nuclear fusion we are trying to recreate in our nuclear power plant? So yes. So with nuclear energy, we have fission and we have fusion. Fission is when you split an atom into two and it creates a lot of energy. How the Sun and other stars creates energy is by making use of fusion. So meaning you are fusing two lighter elements to create a heavier element, and that creates a lot of energy. So what our Sun currently doing that we will discuss in a moment is it's fusing two hydrogen elements, so two hydrogen molecules, to form one helium molecule. And that releases a lot of energy. And that is how stars generate energy. And we will talk about it in a moment. So this diagram, you can go through its own. It just shows the composition of the Sun currently. Sorry, sir, I need to leave you to the lounge closing. I won't be able to join again up until where does sir plan to go? Not very far. So for today's lecture, I'm just going to go to slide number 36. But the recording will be made available directly afterwards. So almost no light emerges from below the photosphere, so you can't see into the solar interior. However, solar astronomers, using a technique called helioseismology, can analyze naturally occurring vibrations in the Sun to explore its depths. So will eventually the sun allow our atoms to combine? Yes, that will actually happen in about 4.5 billion years. But we will discuss that as well. Convective moments of a gas in the sun constantly produce vibrations, rumbles that would be much too low to hear with human ears. And if your ears could not survive a visit to the sun's atmosphere, some of these vibrations resonate in the sun like sound waves in organ pipes. A vibration with a period of 5 minutes is strongest, but that period ranges from 3 to 20 minutes. Astronomers can detect these vibrations by observing Doppler shifts in the solar surface. Helioseismology requires huge amounts of data, so astronomers have used a network of telescopes around the world operated by the Global Oscillation Network Group, or GONG in short. The network can observe the sun continuously for weeks at a time as Earth rotates. In other words, the sun never sets on GONG. Helioseismology has allowed astronomers to map the temperature, density, and rate of rotation in the interior of the sun, as well as to find the positions and speeds of great currents of gas flowing below the photosphere. That information confirms a model developed to understand the cycle of sunspots and solar activity. So here we can actually see it. So here we can see helioseismology. The sun can vibrate in millions of different patterns or modes, and each mode corresponds to a different wavelength, vibration predicting to a different level, penetrating a different level. By measuring Doppler shifts as the surface moves gently up and down, astronomers can map the inside of the sun, which is actually very, very cool. So this is an easy way how we can look at sunspots from your own backyard or from campus. If you have a telescope, you can point it directly to the sun. Just also take note, never, never, never look to the sun with your unaided eye, and never through any object such as binoculars or a telescope. So you point your telescope towards the sun, and just a bit from your eyepiece that's over here, you just put a piece of paper, and then you have your sun on a piece of paper, and you will be able to see sunspots, which is very cool. Another way, which is a very expensive, is you get a specialized solar filter you put on your telescope, and with your solar filter, you can directly see the sun and see sunspots. So I'm going to end off with this lecture, with this slide. So the sun is not quiet. It has slowly changing storms larger than Earth that we see as sunspots and ultimately vast eruptions. In the early 17th century, Galileo observed the sun with a thick dark filter over his telescope and saw spots on its surface. And day by day, he saw the spots moving across the sun's disk, and rightly concluded that the sun is a rotating sphere. And if you repeated Galileo's observations, you would probably also detect sunspots. So question, isn't the sun going to turn into a red giant and grow a lot eventually? Yes, that will happen. So one thing that we will learn in this lecture is what will happen to the sun at the end of its life. So depending on how much mass, meaning how big a star is, there's a few different things that can happen to it at the end of its lifetime. And this is where all of this is building up to. So in these images, we can see when there are less sunspots, the sun has less activity on it. Such as this image over here. If there is more sunspots, such as this image there, we can see the sun is more active. And that is due to sunspots. So ladies and gentlemen, we will continue this lecture next week. I will see you all in class next week. So sir, question, I see we're having about 70 slides per lecture. What percentage of the slides will be actually right on and what is just added information? So if you make your own notes from the textbook, you'll actually see my slides is a condensed version of the textbook. So it depends on your lecturing style, but I will within the week upload the mocks and method test you can use for practice and see how I will ask questions. So Navan, will the sun be a supernova? No, unfortunately our sun won't be a supernova. Our sun is too small to die in a supernova explosion, and we will learn why. So the end of the sun's lifetime, it will just become a white dwarf. So, but we will learn about this in a later lecture. But ladies and gentlemen, thank you for today's lecture. I will see you all in class on Monday. So where can I find the links to the shared recording? So on announcements, you'll see I've made an announcement. And there you'll find links of the lecture recordings as well as the recordings I made during COVID as well. So question, what is the theory as to why the corona is hot? So let me go back a couple of slides. We will discuss that in later as well. So where is that? So that is in this slide over here. But what happens is we realize this solar flares that we have follow over sunspots. And where sunspots is actually a magnetic field line puncturing the photosphere. So this is actually a magnetic field line going out from the surface and then back out. So when we have a few of these these magnetic field lines going out, sometimes they get tangled up and then the material cannot actually go back into the sun again. And that material is what we are thinking is heating up the corona. So is the nuclear fusion caused by the sun due to its immense gravity and immense heat? Yes, those are two of the reasons, but we are still going to talk exactly what fusion is and how it works. So ladies and gentlemen, I'll be active for another minute or two if you have any questions. Otherwise, have a great afternoon, have a great week, and I'll see you in class next week, Monday. So how is it then that we are trying to make fusion happen? So one thing, remember nuclear power that we currently have on Earth is fission. So we take uranium-235, we split it into two, and that creates energy, and that's a chain reaction. So then it takes the next element, split it into two, the next into two, the next into two. So it really creates a lot of energy. But it has its own drawbacks. A much cleaner way and better way is if you take two lighter elements. So hydrogen is the lightest element and the most abundant element in the universe. If we fuse them together, it releases a lot of energy. But a problem with fusion is we need an immense magnetic field to control the reaction. So in theory, we have the physics sorted out of how to fuse two elements, but it's now an engineering problem, is how to create a strong enough magnetic field to create a stable fusion reaction. So actually last week it was news in France. They had the longest fusion reaction that lasted 22 minutes. And then the magnetic field became too unstable and the reaction died down. So that's the one thing we need to figure out, is how to create that stable magnetic field. Question, I have a question from a few lectures back. According to Kepler's laws, the Earth rotates on an ellipse, right? Does this cause any effect on the temperature of Earth? Or is it so minor it has no effect? It is so minor it has no effect whatsoever. What has the biggest effect as is Earth's cant of roughly 23 degrees on its own axis. So that means that cant that it has points the southern or your northern hemisphere directly towards the sun, meaning it receives more direct sunlight. Not closer, but temperature has to do with how much direct sunlight shines on Earth. So the distance has not really that much of an effect. So remember, when we talk about Earth rotating about the sun around Earth, is one astronomical unit, so that is 150 million kilometers. But on its furthest point from the sun, that's about 152 million kilometers, and at its closest point on the ellipse, that's about 148 million. So that's about 4 million kilometers in difference, and that is too small to have a significant effect. So counter question, why does direct sunlight not cause different seasons? Yes, that is what causes different seasons, is how the Earth is canted. So when you have when it's summer in the southern hemisphere, that means the southern hemisphere receives more direct sunlight, and therefore it is summer. In the northern hemisphere, that is now pointed away from the sun, so they receive less direct sunlight, and therefore it is winter. I hope that answers everybody's questions. Sorry, sir, I'm confused because you mentioned something that if we are asked this question, we're not allowed, because I said you're allowed to say of direct sunlight and not due to distance from Earth. So seasons has nothing to do from the distance from the sun. It has everything to do with the cant in Earth's axis. So when it's 23 degrees, that's canted, and that is everything it has to do. So not a distance, but everything with direct sunlight. So question, so then it is just the direct sunlight that causes changes in temperature and not a distance from the sun. Yes, that is correct. So yes, if you look at different planets, then the distance makes a big difference. But on Earth itself, that couple of million kilometers doesn't make that big of a difference. But when you go to Mars, for example, Mars is on average about 30 degrees colder than Earth, and that is just because it's further away. If you look at Venus, Venus is much closer to the sun, and that is about 100 degrees warmer. So it does affect it. So if you look at different planets, yes, that makes a difference compared to different planets, because now we are speaking about a lot of distance. So that is why Jupiter is also planets in our system is freezing compared to the inner planets, which is not. So yes, their difference plays the factor. But just looking at Earth, that doesn't make a difference. Then the distance is too small, and it's just the Earth's own axis. Does that answer your question? So it's just the fact that it's not a drastic enough difference that the temperature is not affected by the sun. Yes, that is correct. It's a pleasure. So if there's no further questions, I'm also going to log off. Have a wonderful evening, and I'll see you all next week in class.